In this lesson, we're going to take some of the ideas we looked at when we started analyzing functions and extend them to sort of more practical situations, and we want to optimize, find the best solution to a problem. But really an optimal solution is the highest or the lowest kind of thing in your model. So when we're creating derivatives, we're creating rates of change in our models. We can apply that to many real-world situations, not just an equation y equals x squared plus 3x. What if we have a real situation based on height or temperature or money or things like that? Well, in each of those cases, if we take our derivative, we've now created a rate of change model which has highest and lowest and highest and lowest points. And we know we can find those if we take our derivatives and set them equal to 0. Okay, so for one example, suppose ht models the height above the ground of a person riding a Ferris wheel. They go up and down and up and down and so on and so on. Well, our derivative would be our height at any single point along that function. Okay. If I want to figure out how the height's changing using my derivative, I can figure out, well, is it a positive, a negative, or a 0? If it's a 0, that means they're at the highest point in the Ferris wheel or the lowest. If it's a positive, that means they're increasing their height, they're on their way up the Ferris wheel. If it's a negative, they're on the way down the Ferris wheel. So we can take the idea of analysis of functions, sign diagrams, derivatives, and actually apply them to real-world situations. So let's try that. We've got the volume of air in a balloon given by this function. Can we find the initial volume? Well, sure we can. Initially, at time 0, put in 0 for all your t's, and you'll end up with 2 cubic centimeters. Can we find the volume after 12 seconds? Sure, we can put in 12 as our t. And a little more complicated this time. We've got to put in for all the t's. That's why the 0 was nice, right? Because it always comes up to 0. And if we put all that into our calculators, do a property should end up with 6,170 cubic millimeters. And just using our function, right? Just points along the graph, if you will. And part C is to find v prime at t and explain its meaning. So that's kind of useful to us. So v prime at t, our derivative, will be 12t squared, so using your power rule, a minus 12t, again power rule, plus 10, and the constant part will disappear, and there's our function. What does it represent? This represents how fast the volume is changing at time t. So how fast is that balloon getting bigger or smaller, as the case may be? Okay, for part D, what is the rate of increase at 5 seconds? Well, there's our perfect example of how we can actually use a derivative to figure out something practical. So if we put 5 into our derivative function for all the t's, we end up with, I got 250. That's millimeters cubed. Now it's a rate, so per second. That balloon is going really fast at that point. It's really getting larger. Okay, that's kind of how we can use our derivative to solve some problems, real world problems. Let's try the next one. The height of a daffodil above the ground is given by this function, where time is in weeks after the plant is broken through the surface. Figure out the height after 2 weeks. Okay, well that's a point along the way. Height at time 2. Put in our 2 and see what happens. If we do that right, I got 38.4 centimeters. After 2 weeks, we reached 38.4. Find dHdW, the height, the rate of the height growth per week. So dHdW. So using our power law again, we got 24. It's just a 1 in there, right? Sorry, 1 times 24. Minus 4.8 W. There's my rate. The rate of growth when W is K is 7.2 centimeters. Find K. So they're telling us the rate. We want to know when that happened. Okay, well, the dHdW represents our weight, our rate, right? So let's fill that in, and let's solve for the W that goes along with it. So we'll get 7.2 minus 24 equals negative 4.8 W. If we subtract that, we get 16.8. And if we divide both sides by 4.8, we end up with W equals 3.5. So after 3.5 weeks, the growth rate is 7.2 centimeters per week. Okay. Okay, more important question to us. When will the daffodil reach its maximum height? So just to refresh with you, this is a quadratic. The quadratic's actually opening down. So it's going to do this. Oh, sorry, opening down. Wrong way. Opening down. Eventually the daffodil is going to reach its maximum height before the growth rate starts slowing down again. I want to know when this happens. In other words, I want to know when my derivative is 0. So for part D, as soon as I see the word maximum, I'm thinking about, oh, turning point, highest or lowest. Okay, so if we take our derivative, which we already calculated previously, dHdW, we make it equal 0, we can figure out where our max and mins happen. Okay, put our numbers on one side, variables on the other, divide both sides by 4.8, and we get 5. So after 5 weeks, it's reached its maximum height. And max after 5 weeks. That's when I reach the maximum, right? The other part asks me, what is the maximum? So 5 and what? Well, if I want to figure out points, I can go back to my initial equation. Our initial equation was our height after 5 weeks. So 24 times 5 minus 2.4 times 5 squared. Just what we did when we made graphs yesterday, except we just have context now, words. Let's find the maximum point. Okay, if you do this right, you should end up with 60 centimeters. Okay, so max after 5 weeks of 60 centimeters. Okay, so we're going to continue looking at some optimization problems. Remember the word optimum means max or min, also knows our optimal value. And one thing I do want to point out, because down the road this might happen, usually your max and min are somewhere in the middle of your function, but sometimes you're given boundaries and your endpoints might actually be your highest or lowest values. So we'll have to think about that down the road sometimes. So, next example. We're looking at the height of a football, and it's given by this lovely quadratic equation. What is the maximum height, and what time does it reach? So thinking about that, football goes up, football comes down. At some point, I reached a maximum. Well, what do I know about that? I know that's the point where my tangent is 0. My derivative is 0. So let's find ourselves a derivative. Now this one isn't in the right order, but that doesn't matter for our derivative purposes. We'll get 28 minus 9.8t. Here is using 1 times 28, 2 times 4.9. I want to know where do I hit the maximum, so I want to take my derivative set equal to 0, and then solve that. So we'll get 9.8t equals 28. And if we take 28 and divide by 9.8, we end up with 2.86 seconds. That's when we hit the maximum. What is the maximum? Well, that's what the original function's for, right? Finding out points. So we'll put a time in of 2.86 for all the t's. 2.86 squared over here. And if you punch that in all in your calculator the way it looks, you should end up with 42.0. Therefore, a max of 42.0 meters after or at 2.86 seconds. Another optimization problem. I'm going to try the next one. The cost in dollars to build a new playground. You model by this equation, where X the number of workers hired to do the work. How many workers should be hired to minimize the cost? Okay, so my graph's going down and going back up. I want to find that point. What do I know? I know that's the point where my derivative equals 0. So let's find C prime. 10x, 2 times 5, minus 70. I want to know where that comes out to 0. I want to solve this. Numbers on one side, letters on the other, divide it out. Okay, now this time we didn't ask what is the minimum cost, it just said how many workers should be hired. Well, X was the number of workers. So costs are minimized with 7 workers. And now if I wanted to figure the actual cost, I could go back to my initial equation and find the point that goes along with the 7. But I didn't ask us for that one this time. All right, last one. It's sort of building us up to what we're going to do next with this. We're going to look at optimizing shapes. So we've got an industrial shed, which has a total floor space of 600 meters squared, and it's to be divided into 3 rectangular rooms of equal size. So let's draw ourselves a picture. It's got to be a rectangle, and you need 3 equally sized rooms. Okay, I've been told the floor space is 600 meters squared. Well, that references area. Area is a rectangle, or length times width. So I know that 600 equals LW. What else have they given us? They told us the walls will cost $60 per meter to build. What dimension should the shed have to minimize the cost of the walls? So I see that word minimize in there. That's an optimal value. But my problem right now is I've only got one equation and it has 2 variables in it. I can't solve 2 variables with one equation. I need a second equation. So what can I do? What can I figure out? Well, let's label this diagram first of all. Call this my width from here all the way across. And I can call this my length. So there's 4 of them, right? And, well, they didn't tell me how much walls I have, but I want to minimize the cost of the walls. So let's build ourselves an equation for the cost of the walls. So what are my walls going to cost? It's going to cost me $60 for each piece of wall I have. How many pieces of wall do we have? We've got 2 W's plus 4 L's. So really, if I expand this, I get 120 W, $60 for each W piece, plus 240 L. That's what my cost is, right? Now that's a second equation with some of the same variables. So here's a nice trick we can use. I can go back to the first equation and rearrange it for one of the variables. For instance, 600 over L equals W. Why would I want to do that? Well, I can now use this equation and replace one of my variables. So I'm going to end up with 120 times W, but W we said was 600 over L. 600 over L plus 240 L. I'm going to simplify that a little bit. So 72,000 over L plus 240 L. Now I've got myself a model for costs in terms of L. What was I asked to do in this question? Minimize my costs. Minimums occur when my derivative is 0. So I'm going to need to take my derivative. Now, before I do that, we don't like derivatives where we have L's on the bottom or variables on the bottom. So let's bring that up to the top and make it a negative exponent. Now we can take our derivative. So I get negative 72,000 L to the negative 2 plus 240. We know we want to minimize this, so we can make it equal 0. And we'll end up with 0 equals. I'm going to fix my exponent again, bring it back to the bottom to work with it, and get this expression. How do I solve this? Well, we put numbers on one side and letters on the other. It kind of looks like we should be able to cross multiply. And sure enough, that's what we can do. L times 240 makes 240 L squared. And 72,000 times 1, well, that's just 72,000. And I can divide 240 out from both sides. So 72,000 divided by 240 comes out to 300. And L will be the square root of 300. Which, if you do that right, you should get 17.32. Okay, so it's kind of a tricky question in that we were having to deal with two variables, which means we had to make two equations. I could sum one equation into the other and then solve, do my derivative process. That's a tricky one, okay? The question says, what dimension should the shed have? Well, we figured out the L dimension. Right? L should be 17.32. Now we need the W dimension. And remember, back up here, we made an equation for W, right? In the red, 600 over L. So W would be 600 over L, which is 17.32. And we punch that in, we should get approximately 34.6. And there's our dimensions. Part B asks, what's the minimum cost? So we had all these expressions for cost. Your choice which one you want to use. I'm going to use this one right here. So my cost when L is 17.32 will be 72,000 over 17.32. That was the first part of the fraction, plus 240 times 17.32, there's the second half of the equation, and we get approximately 8,304. Okay, so our therefore minimum cost of 8,304 when L was 17.32 and W was 34.6 meters. And that's a pretty in-depth optimization question. Tricky, yes, but we should be able to do them. They're kind of all the same once you get the hang of it. Okay, but you definitely should be able to do the ones earlier than that where you're just using the equations. Okay, again, there's a couple word problems to try. If you're stuck, come see me. We'll figure them out together. And then we have one more lesson left in this unit.